All right, and I missed the first part of today's lecture on the recording, but we'll take a look at number 72. Is that an Avogadro's or Dalton's? Uh, Dalton's. Dalton's. Yeah. Dalton's. If we have 1 liter air and it contains 80% nitrogen, how many liters of nitrogen do we have? This is Dalton. This 1 liter of air is equal to how many liters of nitrogen? 1 liter of nitrogen plus how many liters of oxygen? 1 liter. And so if we take all the nitrogen out and put it in its own container, we'll have 1 liter of N2. And then we take all the oxygen out and put it in its own container, we'll have 1 liter of O2. But the number of collisions is going to be way less because, this is missing all the oxygen. And therefore, it's going to be 80%. This is 1 atmosphere, so this is going to be 0.8 atmospheres. And the oxygen is going to be at 0.2 atmosphere. And so Dalton's law says that the total pressure is equal to the sum of the partial pressures here. But the volumes have to be constant. And so this is Dalton's. So we take 1 liter of nitrogen at 0.8 and combine it with 1 liter of oxygen at 0.2, and we end up with 1 liter of air at 1. And so that's true. We have that. The other possible way of visualizing this mixture is via, not Dalton's, but Avogadro's. So what would Avogadro's be? Yeah, so how many liters of nitrogen would we have? Yeah, we'd have 0.8 liters of nitrogen at 1 atm. Plus how many liters of oxygen? Yeah, 0.2 liters of oxygen at 1 atmosphere. And so 1 liter of air is equal to 0.8 liters of nitrogen plus 0.2 liters of oxygen, but it has to be at constant pressure. So there are 2 ways of expressing the nitrogen in air, in a liter of air. 1 liter of nitrogen at 0.8 atmospheres or 0.8 liters of nitrogen at 1 atmosphere. What people tend to do is they tend to get it mixed up. And so this would be true. Okay, other questions?
Could you do 28 in the practice exam?
28. What is the kinetic energy of a nitrogen molecule moving at 3,000 miles per hour, 1,341 meters per second? So I give you the kinetic energy equation on this, so you wouldn't have to have it memorized. But the kinetic energy equation is EK. This is not going to be the average kinetic energy, because the average kinetic energy is equal to the URMS. But this is just going to be 1/2 mu squared, where u is the speed of it. And so it's going to be 1/2. But what do we do about the mass of a nitrogen molecule? Now, do we use the molar mass in this case or the mass of an individual molecule? We're going to use the mass of an individual molecule. The mass of an individual molecule is 28, how many 6 figs on? I'm going to go 2802 U per nitrogen. That's how much a nitrogen weighs. Each nitrogen atom is 1401 U. But the units don't quite work out. This is going to be 1341 meters per second and then we're going to square that. So you need to know the definition of a joule. The definition of a joule is
kilogram per meter squared.
kilogram.
Kilogram meter squared per second.
Yeah, kilogram meter squared per second squared. So we have meter squared per second squared, but we don't have kilograms. So do you remember how to convert U into grams? Avogadro's number, yeah. And so I'm just going to convert U into gram. That is, 1 gram is an Avogadro's number's worth of U. You either have to have this one memorized or you could derive it. Do you recall how we derived this one?
The carbon 12 atom.
Yeah. The definition of a U is a carbon 12 atom weighs exactly what? Is exactly 12 U. And then 1 mole of carbon 12 atoms weighs exactly 12 grams. So we can use these two definitions to derive this. And so we want, let's see, what do we want? Grams on top? So we'll put grams on top. So 12 grams of carbon 12 over 1 mole, carbon 12. Then we want U on the bottom. So we'll put 12 U for a single carbon 12 atom. So that gives us grams per U, but atoms per mole, that doesn't cancel. So I need Avogadro's number here. Avogadro's number says that there are going to be, in 1 mole, there'll be 6.022 times 10 to the 23rd units. And so moles cancel, and the atoms will cancel. And carbon 12 cancels. 12 cancel. And that leaves us with 1 gram is equivalent to Avogadro's numbers for the U. And then we'll convert it to kilogram. So kilogram is 1,000 grams. And that gives us how many joules it is.
He was wrong on that one.
Oh, is it? Okay.
But
Oh, the 1/2.
yeah.
That's right. Okay, so sometimes that happens. What did you get?
I'm getting
So it's
8.37. Oh no. Never mind.
4.18. Is that what you guys got? 4.18 times 10 to the minus 20 joules. Okay, so there's an error in exam. Well, if there's an error in exam, then, and you're pretty positive, you can just write the answer here. 4.18. And that's what people ended up doing. They wrote 4.18. And so that was number
28.
Okay. All right, other questions?
I have a question.
Okay.
Number 87, chapter 5.
Number 87, chapter 5.
It's a double equation problem. I wanted to know how you would do it graphically,
Okay.
or if it could be done graphically.
If you just start off one molecule. And then
Let's start with the goals for what we need. Oh, so you're just like one ball.
Yeah, and then I have kilograms. And I plug that into times 1 times 1341 squared.
So 87, a 0.4324 gram sample potassium hydroxide, lithium hydroxide mixture requires 28.28 milliliters of 0.3520 molar HCl for its titration to equivalence point. What is the mass percent of lithium hydroxide in this mixture? So, yeah, you could do this one graphically. But how? Let's take a look at this one. Well, what's the first thing you would do?
Find the molar mass for what is it, HCl, and
We don't need the molar mass for HCl. No.
all right, we have the land.
I mean, well, actually, before doing any of those calculations, those are the things we'll need for the conversion factors, but
I was to say potassium hydroxide and lithium hydroxide.
Yeah.
I find the molar mass for those
all right.
because conversion factors.
Yeah. Okay, so what we assume is 100% potassium hydroxide, so 0.4324 grams of potassium hydroxide. And then we'll need the molar mass. So,
36.10.
all right, just 10 grams per mole. All right, this is for KOH. And then we'll need a balanced chemical equation for this. The balanced chemical equation is that KOH is going to require how many HCl to react? Looks like 1, because we're going to form KCl in water. And so the 1-to-1 mole ratio. So 1 mole of HCl or 1 mole of KOH. Okay, and then what?
Yeah, so you can do it like this. Start with 1 more HCl, and then you go
Convert HCl into grams using
Not grams.
liters using
Yeah.
molarity.
Yeah, we're going to use molarity. So 1 liter is 0.3520 moles
because it's 1 molecule.
of HCl.
And 2. That's not
And then we'll convert it to milliliters, 1,000 milliliters per liter. Then calculate it. So how many do you get here?
both of them. The gases will
Let me
you know,
punch it in my magical calculator.
into a molecule.
We have 21.89.
Yeah, 21.8967.
89677. So we'll just do 1.896 milliliters. And then we just repeat it, right? For lithium hydroxide, 0.4324 grams of lithium hydroxide. What was the molar mass for lithium hydroxide?
23.95.
And then it's also 1-to-1 mole ratio in form of lithium chloride.
That's
51.29057.
51.29057. We'll just go, yeah, no.
There you go.
So this one's bigger, the lithium. So the way it's set up in the graph is with the X being bigger. And so this is going to be 100% lithium hydroxide. And that's going to give us a volume of 51.29. And this was 0% lithium hydroxide will give us a volume of 21.90. So here we'll try to, well, actually, if this were multiple choice, I'd try to guesstimate it. Because how many milliliters did it take? 28.28. So 28.28 is around here, so it's going to be less than 50% lithium hydroxide. Yeah, it looks like. And so I'd look at the answers and see if they're spread out far enough. Then I already know I don't have to finish the calculation. I can just kind of estimate it. But this is free response, so we have to complete the calculation. And so we do the same thing. We do y equals mx plus b, and then get the slope, which is 51.29 minus 21.90. Over 100 times x plus b, 21.90. We solve for y, or x. We solve for x in this case. Okay. So that's the way I would have done this particular problem. Alternatively, you could do system of equations.
You solve it. Because the answer, they got a higher percentage of lithium hydroxide in the solutions manual. So I thought I got it wrong. That means it should be lower.
All right, so we'll just let me write the equation here. So 5129 minus 21.9 equals 2939 divided by 100, which is going to be 0.2939x plus 21.9. And so x is going to be the volume, so 2828 times times 28.28 equals, and I get 8.3114 plus 21.90. I get an I'm solving for x.
Yeah.
And so this is 28.28. 28.28 minus 21.9. 6.38. And x is going to be 6.38 divided by 0.2939. And so I get an x of 21.708%. It's going to be 3 sig figs, so 21.7% lithium hydroxide.
That's why I got it.
What did the book get?
The book on 21.7.
Yeah, I read it wrong. They actually did give a lower percent. I did it differently though. I went from, instead of doing the milliliters on the y-axis, I did grams, and my calculations were going from milliliters of hydrochloric acid to grams of lithium hydroxide or potassium hydroxide, but I guess I messed it up somewhere, unless that's wrong.
What value of milliliters were you using? This one? 28.28. You wouldn't be able to work backwards from that to the grams. Or how did you do it? Because 28.28, we don't know what that is in terms of how much of that came from neutralizing the lithium hydroxide and how much of that came from neutralizing the potassium hydroxide. So if you started off with 20.28, what would the next conversion factor be after that?
I went to liters after that.
Okay, so that,
Well, and I did two calculations as well. One for potassium and one for lithium. So the potassium hydroxide one
okay,
was, liters and then liters. And then I went 1 liter, 0.352 moles per 1 liter, which is the molarity.
okay. This would be moles of HCl per liter of HCl solution.
And then I did 1 mole of HCl to 1 mole of potassium hydroxide. And then I use the molar mass of potassium hydroxide, so that's 556.11 grams to 1 mole. And then I did that again for lithium hydroxide with the other molar mass.
Okay, so what did you get for this?
0.5585 grams.
And then you just repeated this, except you used 1 mole of lithium hydroxide here for 1 mole of HCl. And then what did you get here?
0.2384 grams.
Okay, and then what did you do? You looked at what we had here, 0.4324, and then you did the percentage, and you got a higher percentage of KOH. Is that correct?
Yeah, I got 60.60% KOH.
Yeah. Yeah, it's let me tell you the situation here is this could potentially work if this were like at the limit. So for example, if we knew that the KOH required 28.28 milliliters to neutralize, but the problem is this isn't at the limit. We don't know what the minimum and the maximum HCl is going to be here. This is somewhere in the middle. And so since it's somewhere in the middle, we can't set these as limits. Like, so for example, if you set this with the maximum amount of HCl, then you could do this, because it wouldn't take any more HCl, but we don't know where that is. And so we can't do this because this is the amount of HCl to neutralize the mixture. And so we're somewhere in the mixture. And so what you're doing is you're figuring out, well, if we're at this point in the mixture, this is how much KOH, if it were pure KOH, but it's not at the limit. And so we can't, but the amount of HCl you use here depends on what the mixture composition is. And so over here, if the mixture composition were pure lithium hydroxide, we would use 51.29 milliliters of HCl. And if there was 0% lithium hydroxide, we would use 21.9 milliliters of HCl. But this is just 28.28, which is in the middle of this range here, somewhere in the middle of the range. And it's not at the limit. And so the problem with doing it this way is we don't know what that limit is. If that were the max, it'd be fine. Now, this is different. This 0.4324 is the max. This is the max amount in mass. We can't go beyond that, and we can't go under that. Whereas this 20.28 is just somewhere in the middle. You know, in the next sample, it could have been higher, and the next sample could have been lower. But, you know, that, in this case, this is fixed in that sense. And so we could get the extreme limits here, but we can't get the extreme limits with 2028, you know, but you're assuming that that's the extreme limit, and this would be it. Does that make sense?
Yeah, so it's like limiting an excess reactance.
Yeah, it basically, that's it. You know, what we do is, everything reacts in this, you know, all the lithium and all the potassium react. It's just that the amount here just depends on the percentage. You know, this one we came up with 21.7% lithium hydroxide. And that would mean it would be 78.3% potassium hydroxide. And that's how much is required to neutralize. So the lithium hydroxide is going to require a certain number of milliliters here. And the same thing, the potassium hydroxide is going to require a certain number of milliliters here. And so both of them react completely. And so if I take this 0.4324 4324 I'm going to get 0.093865 grams of lithium hydroxide, and the rest will be potassium hydroxide.
0.3389. That's not just very significant figures.
0.3389 grams of potassium hydroxide. This is where we are right now. And this mixture contains this plus this. And so what you kind of did in this particular problem is this. You just picked one of these and then said, okay, I'm going to assume that this is potassium hydroxide. And then I'm going to calculate how many milliliters I'll need, although it's going the other direction. And that's going to give me how many milliliters. And then I'm going to take this amount here and then assume it's 100% lithium hydroxide. 3389 grams of lithium hydroxide, and then I'm going to calculate how many milliliters. You know, it's the other direction, but it's kind of the same thing. You're picking this number in the middle and then making the assumption that that's going to border on the extremes, but it isn't at the extreme, it's in the middle. You know, the extreme end would be 0.4324. That's what we should have used. And so if we knew what the extreme end of the milliliters was, we could have done that. But we don't, because and we can't assume that that's extreme, but the 0.4324 we can assume, you know, that's the max amount that we'd use. But this is not the max amount of milliliters that we'd use. And so this is the same thing. This is not the max amount of sample we'd use. We just picked some number in the middle. And this is the number that that mixture had in this particular place, but it's the number in the middle. It's not the max. The max is 0.4324. Does that make sense?
Yeah, so if I were to do it this way, they would have to give me like two values for the milliliters, right? Like
we need to know
of lithium hydroxide and 100% potassium hydroxide requires these many milliliters.
Yeah, or in another sense, we need to know that it generated that many milliliters, you know, of it. And so, yeah. Whereas that number is kind of stuck in the middle, 28, 28. You know? And so the way I see it is, let's say you had a mixture of lithium hydroxide and potassium hydroxide here. And let's say you had 10 grams. And then you pick something in the middle. Let's say you said the reaction. Well, anyway, it's just you're like a number of 8 grams. 8 grams. Well, what does that tell you? Because there could be more than 8 grams. There could be less than 8 grams. But when we said that's only 10 grams of mixture, then you know that there's only 10 grams of mixture. Whereas this number could be more or less. Well, let's do the same thing with milliliters. It could be more or less. But the 0.43 can't be more or less. The 0.43 is fixed. Okay, and you want to start off with the fixed. Okay, are there other questions?
Are you gonna have office hours tonight?
I'm sorry?
Are you gonna have office hours tonight?
Yeah. Well, this afternoon I have office hours.
I have office hours.
Okay, or tonight. Yeah, tonight I can have an office hour 8. If you guys have some more questions. I have this one. Let me hand this back. Okay, Jacob, Tristan, Adrian, Kevin. You can come again. Sarah, Elizabeth, Alex L. Can you come grab? Jose, Sina, Angie, Harandi, Bradley, Teresa, Annalise. What?
What did you do? You do this thing. We do this together.
My name's very basic. That's basically his name.
Alex. Alex. Sarah.
What got wrong?
Lily.
The arrows. I only got weak stuff.
Cassie. I actually. Did everyone get theirs back? Eli and Josh.
Because
Did you do the Lewis acid base quiz?
You don't have to put this in if you don't want to.
Well, you can fix it. Do you want to fix this one?
yes.
We can fix this one. We'll fix this one, and then you can resubmit it. How about that? So I get a question about Lewis acid. I'll just make a new one. I have to find it. Did you turn in the Lewis acid base one? CO2 and water? And calcium oxide?
Yeah.
Okay, yeah. So what do you need to know about Lewis acid base Well, one thing you should know is what we covered in class, and that's about the extent, what we covered in class. And so what we covered in class is, can you recall, when CO2 and water react, can you recall how we did that in class? And so this is just kind of recall. For Lewis acid base reactions, we need to have the Lewis structures drawn out. One. And then for two, we need to draw arrows. And in Lewis acid base reactions, we always show the base lone pair attacking the acid. So we did this. And so a lot of people had it almost like just about. So if we do this step here, we're going to have too many electrons around carbon. We can't have 1, 2, 3, 4, 5 pairs of electrons around carbon, so something has to give. And you got to show what gives. A lot of people had an arrow from the carbon out to the oxygen. We can't have that. One of these lone pairs, or not lone pairs, one of these bonding pairs has to get kicked out and create another lone pair there. And so you have to have it drawn out like this. Okay, I'm going to flip the hydrogen to this side over here. It doesn't matter which side it is because there's free rotation. It's like a propeller. But I had it written differently in class. And then we have to draw non-zero formal charges. So the formal charge on this oxygen is negative. The formal charge on this oxygen is positive. Terribly stable. And then what's going to happen is this lone pair is going to get pushed into this hydrogen here and then kick out these bonding pair. And so you have to show the arrows, otherwise, and then you have to show, all the products. In this case, there's only one. And so we're going to end up with something like this.
Are you missing that?
Yeah, I was missing the hydrogen there, sorry. Well, some people have it just about there, but close. So what we do, this is a part of learning this. You just do this initially, just by copying. And this is like when you're learning to play like an instrument, or you're learning how to play a game or a sport. You just copy certain drills. This would be like a drill you would copy, right? And you make sure you got the drill down correctly before moving on to anything harder. But you need to do something like this, or be able to do something like this. And so, so we did in class, so it's one of these things. Do you remember how to do it? Now, when you read the notes, sometimes it's hard to put it on paper. This is why I didn't like flashcards. When I had flashcards, I would remember it, but I didn't have it into my motor memory. So, for example, when I had an ion, acetate, it always gave me trouble because I remember seeing it on the flashcard, but writing it down on paper was difficult, as then I started getting mixed up. And so this is the type of stuff that you do, when you're going through and reviewing. Can you do this from scratch? If you could do this from scratch, then you're set. So if a question came up on Lewis acid base like this, then you'd have a chance of getting it. All right. So this is just, this is from lecture. And this would be the extent of that. It depends on how many times you see it. You know, how many times over and over you see it. Like calcium oxide, maybe you haven't seen that too many times. Lewis structure for calcium oxide or Lewis structure for ionic compounds. You know. And so some people are drawing, you know, like this, like a calcium oxide molecule. Like that. Calcium oxide doesn't form molecules. So, one thing is you'd have to have the Lewis structure for calcium oxide down like this. This would be one formula unit, but in an ionic compound, in an ionic lattice, we'd have lots of ions packed together in this lattice. One person got this.
You have to draw a lattice.
You should draw a lattice, or you could draw one formula unit. That's okay too. But draw a lattice so you know the difference between a molecular compound and an ionic compound. The oxides can't lead, but we can still have some kind of collision here. If there's a collision here, then there are too many electrons around hydrogen, so it needs to kick some out. We end up with something like this. And so we have this. This oxide gets converted into a hydroxide, so we need to follow it. So I'm going to put it here. This oxide gets converted into a hydroxide, and this water gets converted into a hydroxide as well. And so we need to be able to follow each species. The oxide flux a proton, forms a hydroxide. The water loses a proton, and it's going to form hydroxide. So we end up with two hydroxides. These two hydroxides are going to weaken the lattice. And calcium hydroxide is soluble, so this lattice is going to start to fall apart as we react it with more and more water. And so I'm looking for this. I'm looking for the arrows, and you can get even more, you know, information. So this is -2 formal charge. Formal charges we circle. There's 0 formal charges on that, but we do have delta pluses and delta minuses. And delta plus, delta minus. If you want to do it, but primarily I was looking for the arrows, making sure, and then correct Lewis structures. So, you know, as far as Lewis acid bases go, I could ask you, you know, to sketch, you know, how CO2 reacts with water and the Lewis acid base or calcium oxide reacts with water. You want to be prepared for a question like that, like on a test, in which I've asked in the past. I've asked actually these 2 questions in the past on tests. It's a quiz, so it was also a quiz, so you want to be prepared for that. Can you repeat this, you know, on paper? If you repeat it on paper, then you know that's step 1 of being prepared for Lewis acid base. I could throw in an advanced problem. An advanced problem would be like rather than CO2, I'll pick sulfur dioxide. Sulfur dioxide has quite a bit different Lewis structure. But what would the mechanism of that be? These are called the mechanisms. This is what you do in organic chemistry.
One of my friends was taking organic, and he was telling me about which I was actually wondering what you were talking about. They told me there was organic decomposition.
Yeah, this is This is organic chemistry here. You rearrange the electron pairs.
Make something new.
Yeah, to try to make something new or figure out reactions. Do you see they're putting formal charges there? They're also using a lot of abbreviations. Not everybody abbreviates things this much, but
I think it's meant for simplicity. Help us understand.
yeah. Do you see all the arrows and stuff?
Look at all that whole line.
This is the type of stuff that we do here.
See it now.
So you could fix yours and turn it in after spring break. Have it, and then I'll grade it. Okay, were there other questions? Looks like we're out of time too, so how much time do we have left? 3 minutes?
3 minutes. 3 minutes.
3 minutes. If we have 3 minutes left, then let me use that. Well, anyway, you're going to have chemical reactions on this test. And so, did I already tell you what the reactions to expect? Pretty much. You can do it again. A sprinkling of all of them. But you'll also need to know nomenclature and some solubility rules for this.
Are we gonna have like a section for nomenclature like that?
No. The situation though is for the chemical reactions, I'm going to give you the name, but not the formula. And so you have to, first step is to write the correct formula. And so you want to review some. But then again, it's going to be, if I'm going to ask you let me just give you a hint here. If I'm going to ask you to do a chemical reaction, most of the species are going to be on these two charts here. And so, like, for example, sulfate. Is sulfate on this chart? Yeah, it's right here. And over there. Or other things. So a lot of the species are on this chart. And so it's always, I don't know what happens, but sometimes people get stressed out and they don't write the correct formula. So for example, ammonium or ammonia. I mean, ammonia is here on the chart. You can just look it up. And then make sure you get the correct formula on the chart. The charges on the ions, people mess up a lot too, but all the charges are here. And so you can essentially look it up. And so I think I told you, I gave this chart out, and fluorine's one of the biggest, but the person got fluoride as F2 minus. I don't know how they got fluoride as F2 minus. But I think it's some kind of tunnel vision, or stress during the exam. It's here and there. So if you're still struggling with nomenclature, there's some big help here on this. So I don't want to see too many, hopefully, errors in nomenclature. Anyway, good luck tomorrow. And then I'll have the office hour this afternoon and then tonight.